diamond, a lead pencil, a chunk of charcoal. Three different things, yet chemically the same element, carbon. What makes them so different from each other? Of the three allotropic forms of carbon, the diamond is the hardest. In fact, diamonds are the hardest substances known. Diamonds are nearly pure crystalline carbon. Besides their desirability as gems, diamonds are also valuable to industry because of their hardness. Abrasive wheels containing diamond grit are widely used for grinding hard substances such as metals, glass, stone. Harder than any of these materials is the diamond, almost pure hard carbon. Now, what of the lead pencil? The so-called lead is really carbon in a softer allotropic form, graphite. Graphite differs physically from the diamond, but chemically is the same, almost pure carbon. Besides its use as a writing material, graphite has a number of other uses. It is slightly slippery to the touch. When powdered, graphite makes an excellent lubricant. The diamond is the hard form. Graphite is a softer allotropic form of carbon. Charcoal is one example of the third allotropic form, amorphous carbon, which is very soft. Amorphous carbon is an extremely black substance, which in the form of lamp black or soot is widely used as a pigment in paints and printing inks. This is the most nearly pure form of amorphous carbon and can be obtained from any kind of animal or vegetable matter. Sometimes the soft amorphous form appears hard, as in coal, which is mostly carbon, vegetable matter that has been compressed over a period of centuries. In the glowing coals, chemical reaction produces carbon monoxide, CO. This inflammable gas burns in the presence of more oxygen to form carbon dioxide, CO2. Carbon dioxide is a colorless, odorless gas, and in contrast to carbon monoxide, it is non-inflammable. It does not burn because carbon dioxide is itself the final product of combustion. CO2, compressed in steel cylinders, has many uses. When carbon dioxide is forced under pressure into water, it reacts with water to produce H2CO3, carbonic acid. You will find a cylinder of dilute H2CO3 behind the counter at your neighborhood soda fountain. When pressure is released, the reaction is reversed, and the carbonic acid quickly goes back to water and carbon dioxide. This reaction causes effervescence in carbonated beverages and changes the taste. Besides combining with oxygen, carbon combines with many other elements. For example, with chlorine to form carbon tetrachloride, CCl4, and with sulfur to form carbon disulfide, CS2. Both are very volatile and widely used as solvents. But carbon disulfide is highly inflammable, while carbon tetrachloride is often used to extinguish fires. The compounds of carbon are more complex in such things as petroleum. Here, carbon is combined with hydrogen in the form of hydrocarbons. Petroleum is a mixture of many different compounds of carbon and hydrogen. Hydrocarbons and compounds derived from them are known as organic compounds. From just carbon and hydrogen come many thousands of organic compounds. How can this be? For our answer, let's examine the carbon atom itself. Of course, you can't exactly see a carbon atom, but we can represent it something like this. Carbon has a valence of 4. That is, it attaches itself to other elements through the sharing of electrons by 4 covalent bonds. The element hydrogen has a valence of 1, so the simplest hydrocarbon is a combination of 1 carbon atom and 4 hydrogen atoms attached by single bonds, which may be represented like this. This compound is methane, CH4, sometimes called marsh gas. All the atoms are connected by single bonds. Carbon atoms also have the property of attaching themselves to other carbon atoms to form more complicated compounds. Thus, 2 carbon atoms and 6 hydrogen atoms may combine to form another compound. This is ethane, C2H6, and is known as a chain compound. Propane, C3H8, is obtained by adding another link to the chain, and butane, C4H10, by adding still another link. As more links are added to the chain, many complex compounds are formed, all from the 2 elements, carbon and hydrogen. In addition to chain compounds, hydrocarbons have other arrangements. For example, ring compounds. Benzene, C6H6, is one of the simplest of these ring compounds. Note the double bonds between some of the carbon atoms of this compound. At times, carbon atoms are attached to each other by triple bonds. Acetylene, C2H2, is an example. Another factor accounting for the tremendous number of organic compounds is that the same atoms may be arranged in different ways. Take butane, a regular chain compound we've already seen. These same atoms may be rearranged with a side chain to form isobutane. The chemical formula is still C4H10, but the properties are different. These variations are known as isomers. Some organic compounds have hundreds of isomers. So much for hydrocarbons, that is, compounds of carbon and hydrogen alone. Adding still another element gives us many more organic compounds. Let's go back for a moment to our simple methane molecule, CH4. The addition of 1 atom of oxygen to the structure gives us a completely different compound. This is known as methanol, or wood alcohol, CH3OH. These 3 elements are the material